Hello and welcome to this month's coffee break. My name is Andrew Miller, your host, lead principal technologist here at Pure. I'm really happy to be joined this month, as I always am, by an amazing guest, Pete Kirkpatrick. First heard him present back at Tech Field Day, for those of you who like that venue, and I actually really enjoyed his depth and his, I think, mildly snarky sense of humor, if it's all right to say that. But, it kind of came out, and so just like, like we enjoy what we do. So today we're going to be talking about love software, make hardware, behind the curtain of Pure's hardware labs. And I'll pull the music down here a little bit. We'll let it keep going at the end. A little bit of housekeeping before we dive in. So as always, this is a series. Thank you for coming back for month 31, if I've calculated it right. You can always find previous months due to the solution focus, I think, and I've had feedback from others that they've aged quite well. Actually got a lot of feedback from folks at Accelerate last month, which was really cool, about how they enjoy Coffee Break and found the content useful over time. Keep up to date with the industry and with what Pure does. You can find previous events or register for new ones at purestorage.com events. You can also find previous coffee breaks listed there as well. And while we're not going to play this month again, the promotion video from Accelerate, I do want to make sure to highlight that the day 1 and the day 2 keynotes are on YouTube, as well as available, as well as you can actually find all of the on-demand sessions, all the breakout sections actually available on demand. Those are with audio and with slides. So there's a lot of really good content there, including, actually, if you were there, you might recognize some stuff that Pete did over there. You'll see that a little later on, because we borrow from previous work. As always, for some of you, and I can appreciate this, you're here for the gift card, some details there. You can see this in the follow-up that comes within the next week from Olivia at Pure Storage. There are some exclusions here. We appreciate everyone in this list attending. You just know why we can't send you stuff. That's how life works. As I mentioned, my name is Andrew Miller, your host. As always, I'm not going to say a lot about my background. There's customer, partner, and tech marketing. But in this case, we're talking about kind of hardware labs. And I remember my first time, this was actually in a data center. I just graduated from college, got my first IT operations job. And I walked in the data center and they said, here's the data center. And then they opened I thought the rack, 42U rack was actually the computer, the server. And I come out of help desk background, and then they opened it up and it was like, wow, there's all this other stuff inside it too. It's like, look at that, so I started like way back. I've come a little way since then, but there's been this fun sense of enjoying hardware and rack mount stuff, and even HVAC and all the cooling that goes into that. We're going to explore those themes as we go along the way. Pete, we're going to wander through some of your professional history, but there's Pete as a person, not just Pete as a Pure employee too. So you mind giving a little bit of your background here?
Yeah, this is fun because I thought back to all the jobs I've had, not just the technical stuff. And, I've had a lot of fun. Some of these are more fun than others, especially, working in agricultural fields or cooking for folks. It's important life stuff. But as it's evolved, it got more and more fun, I'd say. Definitely skiing and rafting were kind of highlights, but now those are more my hobbies rather than how I make a living. But a little bit of science, a lot of technology, and having that evolve over the years has been it's been really, really thrilling. And now I've got a family. I got my 2 teenage boys who are just amazing, and spend a lot of time with them, and we do a lot of these activities together, and it's just been a great ride so far.
I was going to say maybe you peaked a little bit early with Ski Bum and Raft Guide.
I know.
But if you're doing it again with your family, then no, I guess not. So
absolutely.
Actually, I have a cousin he's done that for years on the side. He enjoys it. He's really good at it. So last housekeeping note, next month, as this is a series, please join us again. It'll actually be with our 3rd-time guest, Jack Hogan. Data center fatigue, or maybe data center decision fatigue. So many choices. You need a bridge to the cloud, a cloud bridge. We're going to explore yet again the theme of making the cloud fit your business. Some of what we've been hearing from the last year about customers on their cloud journeys. Some of the kind of the phases of cloud journeys that we've seen, the 6 states of the cloud journey, from analyst and customer perspective. And then, of course, as always, some new announcements from Pure in this area overall, cloud capabilities, and especially bare metal as a service. So with that, on to the topic, love software, make hardware. Now, for those of you who are thinking, as someone asked for an agenda earlier, here's the agenda. It's the same kind of simple format as always. Not too much like it says. And hopefully you kind of recognize the title as being related to this quote. People who are really serious about software should make their own hardware. Maybe you know who that's from. We'll check that in a minute. We're going to first, as often, start with a little bit of exploring some of your technical background, Pete. Kind of quite a ride, lessons learned, some of what you've done over the years. Then wander into a little bit of alphabet soup and technology inflection points around NVMe and TLC and QLC. Then going into direct flash, the origin, some of the gutsy bets behind Pure saying, and actually you were instrumental in this, Pete, deciding that we're not going to continue to source SSDs. We're going to make almost our own equivalent, if you will. And then, as always, a little bit of what's new and the accelerating pace of hardware platform innovation. We've got some great folks online. Sean Kennedy, I think Tago's joining later to be able to help with Q&A in the chat. Please feel free to put stuff in the Q&A if you have specific questions. We will, as always, try and end about 45 minutes after the hour, give or take, and then we'll hang around for Q&A and kind of let our hair down a little bit and relax. But first, before we dive in, Olivia, if you don't mind tossing up the first poll. This one has no commercial value to Pure. We're not gathering your data for any specific reasons. It's just to have a little bit of fun. So on that quote, who said people are really serious about software, should make their own hardware? I think that was you, right, Pete? Am I correct in attributing that to you? Okay.
I may have said that from time to time.
Yeah, actually, I know you have. I've heard you say it. Now, were you the first one who said it? No, that's an more interesting question, but hey. So we will just leave that up and feel free to fill that out as you chime in. No matter when we close the poll, it's always a little too late, but we'll leave that up. So first, thinking about your title, VP, Chief Platform Architect. You don't just jump from college to doing that, but I'm kind of curious a little bit of what does that mean? And then we're going to wander into a little bit of how do you get there. So maybe just start with a little bit of a description of what you do, and then maybe we'll start out back in the days of when you were at NIST.
Yeah, cool. So, the platform is, I think it's a term that's a little overused and pretty heavily loaded. So no matter, where you are, somebody's going to call something a platform. But, what I think of it as it's the hardware, right? It's, some of the products work on a box. This is a box. So it involves all the physical stuff, everything you can see and touch. But, you can't have all of that work without software that's embedded in it and the application that it's designed for, and even thinking about the environment that it fits into. So that's kind of what the platform is to us. I feel really fortunate to be an architect. Architects, the way I say it simply is architecture is how it should work. And any engineer on the line that hears the term should work is immediately skeptical. But I actually mean that. It's how it's supposed to work. But it's not the full design, right? And so there's a huge amount of work and folks that take this idea of how things should work and turn it into something real. And I think, as far as how I got here doing this, I think probably the number one thing is you gotta like people. You gotta enjoy working with people and talking with folks, because it does take that whole village. You need to talk to the end users to find out what they're trying to accomplish. You got to talk to all the folks in all the adjacent areas to figure out what's possible and, what we could get done, and it's got to be done in a certain time frame. And so you've got to balance all of these different factors, and that requires a lot of people and time, spent balancing those factors with folks.
I think you're saying people skills and being able to, I can talk to people. A little bit of an Office Space reference there too, even with the technology.
For sure. And when I came out of college, I would have put it the other way. I'd say, oh, you got to know all this, technology and you got to know things and do lots of math. And it's flipped to it's really a people thing.
So when we were thinking through and looking a little bit, you actually started, or it's been a little way back at NIST, working on superconductors. You mind kind of describing that a little bit?
Yeah, that was really fun. And it was pure science for science sake. And I was young then, and so it was kind of a practical focus. But we did superconductors, and it's funny because it was called electrical transport, which I think of as like a wire is how you transport electrons. But these were pretty sophisticated wires. There's a lot of flavors of superconductors, but they only work under certain conditions, certain current and certain magnetic field and pressure. And there's a lot of things you can do to these to make them go normal and not be superconducting. But probably the coolest part is the research we did led to the development of the wires that make up the giant magnets in particle accelerators like CERN. And so when you work in science, you might do some pretty fundamental little element of it, and it gets built up into something that can lead to some of the most fundamental discoveries in physics. And so that was a real eye-opener. But at the same time, I remember when I went to the head of the department and I told him I was going to move on, focus on what I was doing in school, which was electromagnetics. And he said, no, you should really focus on superconductors. It's the future. And it has come a long way. We have maglev trains and all this cool stuff. They're even talking about building, transmission lines for superconducting transmission lines for power delivery. And it's amazing. But I think I wanted a broader view of the world. And so I moved on into different areas. But I really appreciate doing that stuff. I kind of cherish that time doing science.
I think some of that actually, if I'm not mistaken, some of that foundational work led to the Higgs boson particle development. I feel just intelligent saying that. For those of you out there who know what that is, we're not going to try. Actually, put that in the chat if you know what that is. That feels like it's worth a bonus gold star. Just feel good. As you were shifting though, so superconductors, electromagnetics. I mean, there was even some level of thinking about technology in isolation to even starting to think kind of more as systems or systems theory.
Yeah, my first real technology job was it's really product focused, right? And so as soon as you're into industry, then you're making a product or a service, and as someone coming out of school, you got to focus, right? You don't know everything, you can't know everything, and so you got to be ready to learn, and you probably get a smaller job. And in the beginning, I was designing optical communications. Some of it was down at the laser and detector level, but pretty quickly built those into modules, built those modules into transceivers, and what today you'd think of as the transceivers that plug into all the ports on a switch or a server.
SFPs and
I was involved in the very first 10 gigabit Ethernet transceiver. And believe it or not, those things that you can get for $50 today, we used to get paid, $15,000 to make a single one, and it didn't even plug in. It was so anyway. That's just one example where that's like one of 100 technologies that I work with today that I happen to get really deep on. But as you build up experience in different areas, you end up being able to put those together. That's what a system design does. And you'll probably hear me say a couple terms over and over today, like balance, efficiency. Those are really critical in any one of those areas. But when you put them together, the balance between all the components and requirements and the efficiency of how things work becomes super critical. So networking, computing, storage, I've kind of had a lot of those experiences, and now again I feel fortunate to be able to kind of all apply it all in the same area.
I think of sometimes architecture or design is even, you can say it the nice way, is what do we optimize for, but it's also what do we don't optimize for. What do we choose to waste? We may choose to waste certain things or not optimize for certain things because they don't matter. Optimize for sometimes we don't optimize for time. Like it'll take a lot longer to do it. Make it easier for the system. That's a little bit of a teaser for Evergreen later. I mean, maybe last piece in this section, if you don't mind, Pete. So depth in hardware, even applied versus theoretical science. I'm losing my terms, right? Pure science kind of thing, but moving to the applied stage. Why come to pure as frankly, when you came here, Pure had no custom hardware, totally a software company. Obviously, it was the beginning of the era of Flash, but Pure didn't make Flash or even anything beyond the software. So why does someone who's deep in hardware come to Pure?
Well, a lot of those other factors that I mentioned, the people, I started talking to folks, and I even told everybody what I really didn't like about my current position at that time. And they told me that everything was different here, and the people, learn from each other and support each other and respect each other and take responsibility. And then I thought, well, I just told them all the things that I was looking for. And of course they said that's what it was like. But now it's 10 years later, and I can guarantee you that has come true and over and over. So that people thing is critical. We have a fantastic team, but in one sense, I remember actually really distinctly. I was sitting around with a brilliant architect that I worked with at the time, and we were watching some of Pure's videos, and some of them are just funny, but some of them were kind of architectural, and they talked to them about how they designed the product, and at that time it was all software based. And we were sitting around and we saw some of the capabilities that they demonstrated, and this architect said, how did they do that? And for me, that was a really distinct moment where if somebody really smart is that interested and then is a little bit baffled about how they accomplished it, I knew they had something special before I ever joined. But the fact that they didn't have custom hardware was also a huge opportunity, right? And so taking the fundamental value that was honestly a bit closer to the application, where value kind of does flow from what users are doing, having a fundamentally great software architecture and having it on unoptimized hardware was a huge opportunity, and I could see that we could do a lot to improve it. And at the time I worked with Bill Soretta, and he was interested too, and both of us joined Pure to kind of do this custom hardware thing, and now we haven't looked back for 10 years, and it's been really great to kind of combine the value of hardware and the value of software and co-design and make that all work together.
There's huge value in the co-design. We've explored that in previous, actually Justin Emerson called that out a lot. I think the only other piece on here I just want to make sure to mention is that one of the core pieces that you mentioned, we'll get to section 2 here, is that Flash had such a huge performance advantage, 1000x, that we could actually throw away a lot of the benefits for the economics. So we could actually, yes, it's so much crazy faster. We can choose not to optimize around certain things for the economics. The fundamental problem 10 years ago, even now, was cost. And so obviously dedupe compression helps there. But we could actually, Flash had such an advantage, we could then optimize around other areas to make it fit, kind of thing.
That's right.
Cool. Okay. Into section 2. Hopefully I'm not leaving out anything you wanted to say. It's always a little loose, as folks know. We kind of planned it out, but not too much. So let's think about some of those technology pieces. Maybe that almost kind of, I think of it maybe as technology building blocks. NVMe is in there. We could say QLC, TLC, Flash generations. We could say PCIe. There could be other ones. I think there were 2 main ones we wanted to explore for folks that really kind of just a hardware and I don't know if it's, I guess standard level would be the right term. Maybe let's first explore NVMe, and actually maybe I should do a little bit of a brief introduction there. So for folks familiar, you have SCSI, and actually maybe you can give me a grade on this, Pete, see how I do. So SCSI is serial. It's actually, I think, Shugart all the way back, like SCSI. And so it's built originally more for disks, especially than for Flash. NVMe starts to have lots of lanes and basically can be highly parallelized. So there's an impact here as far as latency and parallelism that fits Flash. I'll let you keep going there, Pete, and both you can correct me on what I said if it wasn't right, as well as
that was exactly right.
And the impact on Pure and what you've seen. So please.
Yeah. And I think it's a good example. I think anybody that's looking at it right now probably just considers NVMe the obvious choice. If you're working with Flash, it's undoubtedly the most popular, the right interface. But if you rewind 10 years ago, it was fringe, and there's always new technology. There's always multiple candidates for new technologies, and Any one of them probably gets some degree of hype, and it can be very hard to tell what's important, what's the trend, what's going to happen, what's not going to happen, and you don't want to jump on the wrong boat, right? You that can sink a product, it can sink a company if it's a startup. So you have to treat these things really seriously, but you also can't perfectly predict the future. You have to kind of rely on fundamentals. And so we certainly believed that Flash was the future. There was no doubt about that. I had learned that before I joined Pure. It was why Pure was founded. It's why we, got together. This is our whole mission at the time. But the technology was actually based on SAS and SATA, which, was those are SCSI-based technologies, and those were a good bridge or a transition from disk, right? Because the compatibility with the old technology enabled you to fit right in, bring some of the new benefits. And, not everything is perfectly optimized, but that's kind of how these transitions work. Compatibility can be even more important than having all of the perfectly optimized things that you may get later.
Mm-hmm.
So again, it was a bet. We made a bet, but we looked at the fundamentals and said, if Flash is going to happen, a lot of the benefits derive from having high amount of parallelism, lower latency, and the SCSI technology was at odds with those fundamentals. So following those down into the depths of the protocol that's exactly what NVMe is designed for.
Yeah.
And so our challenge was, how do we do both? How do we have the old technology and then make this bet on new technology, but let's not redo things every time. We wanted a way to get there fluidly, more like you do with software, right? So good software can be updated in place. You don't want to disrupt your application to make the transitions. We wanted to do that with hardware, which might seem a bit funny, right? Because hardware is a physical thing. You got to get the new thing in and the old thing out. But the way we approached that was just to build both into the system and then start using NVMe where it mattered the most. And so we actually started with it in our NVRAM where performance is critical.
Yeah.
Later, we moved that into the drives, and now we've got it at end to end, right? We've got all of the flavors of NVMe fabrics, front end protocols.
As well.
And so the bet paid off, even though it wasn't obvious at the time. And now the system is essentially 100% NVMe. And even though there's still SAS in there, it's been a decade, and we still support the SAS that we did at the time. And so I think that's just a great example of how a transition happens. You don't drop the old and grab the new. It really is a gradual transition.
Sometimes that feels like the definition of an enterprise company versus consumer. Sometimes you see stuff even in software land. I'm thinking of consumer companies, they drop off support, but enterprise, we can't do that. Like, businesses rely on it. I was pretty sure that you had an Evel Knievel reference there you wanted to work in, just maybe.
I love that one. Yeah. Yeah. Some people say like crossing the chasm, which I think is a great, it's a little bit more of a business analogy, but I'm from Montana. And so my fellow Montana, Evel Knievel, is famous for trying to jump the Snake River Gorge in Idaho with a rocket. And so that's usually what sometimes it's when I'm trying to discourage people from making a big transition. I use that because he didn't succeed. He didn't die there, but he definitely didn't make the jump all the way across. But you can't take a risk that big in this kind of technology world, especially in the enterprise, but even in hyperscale or other places. You've got to know how to get from A to B without completely failing, or you may find yourself in trouble.
The other thing I think of there, and now I want to give credit to Mike Richardson, who I borrowed this phrase from. He's at Pure, previous PT, and has responsible for America's pre-sales, talks about how our problems, as technology companies, and sometimes these are like major technology paradigm changes. Our problem shouldn't be your problem, shouldn't be a customer's problem. It's our problem to figure that out, not to say like it's your problem, you have to move all your data and migrate and rip stuff in and out. Like, we should facilitate those technology shifts for you.
Right.
I think the one other part here to explore a little bit, Pete, is just even kind of a little bit of flash generations. I'm going to jump in the time machine here. So folks who have joined us for a while
Uh,
have seen this slide before. Actually, JD and myself in the second coffee break ever, we were walking through QLC and the launch of FlashArray//C. But do you mind kind of highlighting, there was, and this is briefly, we'll see if we can make up a little bit of time here, but what were the major differences between MLC, TLC, and then QLC, kind of the engineering level that you're having to deal with? Because there's
yeah.
even some a little bit unexpected there too.
Yeah, that's been a fascinating journey. In terms of transitions, the macro is hard drive to flash. The whole world has been moving, and the end is near. We may talk about that a bit too, but these are more, hey, like you talk about Moore's law, and that's actually a collection of thousands of technologies that allow the trend to keep going. So these transitions were more, clearly you were using flash, but the main trend again was economics. How do you take this great technology and apply it more and more broadly? Well, you make it cheaper. It did have performance to spare. I think you could argue it still does have plenty of performance to spare, but if you go all the way back to SLC, there was no way to take advantage of all the performance of SLC at a system level, especially when folks were used to older technologies. It was, you can't take 1000x jump in all areas of a system at the same time. So you put in the new technology and then have everything else kind of catch up. Mm-hmm. But really the meaningful start of flash as a storage technology was with MLC. And looking back, it seemed hard at the time, but looking back, those days were easy. MLC flash would arrive off the truck with no errors. You could read and write to it with no errors in the beginning, and only, towards the end of life, you'd start to deal with errors. And so the encoding was easy. But MLC was also associated with the planar, the semiconductor, architecture was planar, two-dimensional. Mm-hmm. And so you just had cells that would hold the bits, and they would shrink and shrink and shrink. And the cool physics thing there was that they shrunk small enough to where they only held, maybe 100 electrons, something like that. And there's a term called critical electrons, which meant that if you lost track of, say, 10 of those electrons, we're not used to counting those things as individual things. You can count those on both your hands. If you lost track of 10, you had errors. And so that was really clearly the end of that era, because the end of the 2D era, because, it's electronics, you're storing electrons, and when you go below that limit, you're gonna have serious problems. And so the transition from MLC and 2D scaling transitioned both at the same time to kind of TLC, which is 3 bits in one of those little cells instead of 2 bits, but also to 3D. And now the whole world runs on 3D flash. And really what that means is the semiconductor architecture went from two-dimensional and everything was defined in 2 dimensions to now stacking layers of those cells along a column. And the cool part was putting 3 bits per cell instead of 2 bits per cell should be a really difficult problem in terms of signal to noise and errors, right? But because everything had scaled down so much in 2 dimensions, when we got a new vector to scale in a 3rd dimension, we backed off a bit, right? We backed off and made those cells big so they became easy to work with again. And then we've been scaling in that TLC world for, 8 years or so now. And that actually made TLC a lot easier to handle than a lot of us expected. Mm-hmm. Okay, but we got used to that, and then along came QLC, and in the beginning we just said, well, that's not useful. It's rotten. It's full of errors. It doesn't have any endurance. So if you use it too much, it'll wear out. It's slow. But we realized at that time that there was a huge opportunity. Still, again, we're chasing the economics, and so we decided to embrace all the characteristics of QLC instead of trying to compensate for all of those problems, at least the performance and the cost problems. We embraced it. We said, let it be slow. Let's actually put slow controllers in front of them, because if you have slow media, you don't need a really high power controller. And that enabled us to kind of multiply the benefit of the economics and make the whole system cheaper. And that was the FlashArray C.
Mm-hmm.
But meanwhile, it didn't replace everything like in the earlier transitions. And so with the other transitions, everything moved to the cheaper stuff. We saw it as an opportunity to say, let's do two systems. Let's make a low cost and somewhat slow system, but then maintain the need for transactional systems. Anything that worries about performance should still run on TLC. And we've maintained that both in parallel for several years now.
And that has even been now as that feels like a segue to how we made some fundamental bets and then also accelerated actually some of the platform development. The only other piece here I want to mention is for anybody if you're following along, there's a shift from 2D to 3D, MLC to TLC. If you have ideas about how to make Flash in 4D, please reach out. We'd be happy to help you file some patents on that, kind of thing. Because that would be the next major jump. That's about as nerdy a joke as I'm ever going to make, I think. So, hey, I feel like I should get points for trying.
Love it.
So I think if it's all right, Pete, we'll actually, Olivia, if you don't mind closing the first poll and just popping the results back up there. Thank you. So, so for anyone wondering, man, it's not actually. So I can understand the Steve Jobs answer. Where I first saw this quote was actually Steve Jobs in a keynote because I worked Mac Help Desk and used Macs a lot. So I saw it from him. But that quote is from Alan Kay, actually, believe it or not. So, and actually go ahead, Olivia, if you don't mind, and start the second poll, and we'll get into section number 3 here. So curious, and we will share this back so you can see what everyone else is seeing too. I've got over 1,000 folks on today. What's the biggest SSD or flash module in your data center today? Curious. And then do you see ever buying a hard drive again for your data center? And we'll just let that play out. So obviously a lot of flash engineering and understanding flash, even when we were doing SAS or we're doing SSDs, right? Where it's a kind of a miniature storage controller and there's reverse engineering going on to figure out what that looks like. But I almost want to kind of jump into a little bit of the history of, well, I'll just leave it here for a second, slide whiplash. Oh, well, direct flash 10 years ago, because it was really 10 years you started thinking about this. That feels like a pretty gutsy bet. I mean, Pure's just barely launched even, right? And you're starting to kind of paper a pen out what this would look like. Take me through, how the decision process, if you don't mind, around deciding to start with making our own flash modules, and then even a little bit of the history there too before we talk about all the benefits, but I'm guessing they'll blur together. So what was the decision process like?
Yeah, that if we thought NVMe was a big bet, that was a standard. At least this is this is real invention, right? So we started from scratch, and again we relied on the fundamentals that we had the right trends. Flash was going to take over, and that yes, emulating hard drives using SSDs, which is really what they do, is a good way to transition because the whole rest of the stack knows how to operate on top of that. But that if we had the fundamentals right and we were planning for success, that optimizing for flash would bring out a lot of efficiencies and all sorts of other benefits. We'll try to kind of show how those have come true, which is, when you're trying to get something started, you have to kind of promote it. You have to make some claims about things that aren't true yet. Hopefully they come true. Hopefully they don't.
Yep.
And this one, the fact that we're sitting here and you can tell that in the beginning there was almost nothing, and now all of Pure's products are relying on this technology kind of optimized in different ways. It has been successful, so we can look back about those claims and kind of celebrate how we got some of those things right. But this one took a village, just like everything else. And our founder, Cause, likes to say, oh man, we should have just done all this in the beginning. We should have, we shouldn't have waited until 2017. We should have shipped it, early on. And I'm very careful when I disagree with Cause, but the fact that we built the system, got it stable, started to scale the business and the product line, before we took on this step, I think was actually a prudent choice. It could have been too much to do all at once, but we did a good job of the system side, and then we were able to do a good job based on that stability. We were able to do a good job on direct flash. really what happened here was, again, SSDs were emulating hard drives. And what that really means is you fire up a hard drive and you get a certain amount of capacity. You can read and write through that whole, linear contiguous address space, kind of however you want. And Flash at the very bottom, it just doesn't work that way. You have to erase large parts of it before you can write to other parts of it. And you can't, that's asymmetric in terms of the size that you write and the size that you can read back and the size you can erase. There's all sorts of these quirks down at the very low level. For most of you out there, you're probably happy that we just hide all that from you, but this is what we do.
That's our job. Yep.
And so optimizing for how it actually works, instead of faking out, another interface, what's kind of the insight. And further, the system, any system, already has that level of abstraction from the space that the user sees down to some other logical space, and then down to the physical space again, has these maps where you need to map all of those spaces together. And so we just decided that completely eliminating one layer of that mapping and all of the work associated with it, in this case, it's garbage collection. Whenever you have a map and you're reading and writing on a different level, you end up having to collect the garbage that you've created in that process. We literally eliminated that completely. And so a direct flash module doesn't do any of that work at all. It turns out that it's dramatically simpler, it's dramatically more efficient, and these are the benefits that ensue from that decision.
Felt right.
And so instead of kind of designing around all of these goals, we got that fundamental architecture in place, and these are the things that naturally come from it. I think we'll kind of touch on how we get to each one of these things, but efficiency, the bottom one says efficiency, but all of these things come from efficiency. They just manifest in kind of all different ways, but not having the map from the logical to physical space means that a traditional SSD will use roughly 1,000 to 1 flash to DRAM ratio. And the DRAM is required to hold the mapping from the higher level. We don't have that map. We still use a bit of DRAM, but we get to use it for, I think, much more exciting purposes. Caching and buffering and things make the system better instead of doing this mapping functionality, which doesn't really give you any benefits, something you're just forced to do. But that lack of reliance on DRAM means that, just think, if you want to make a 150 terabyte flash module, that means you need 150 gigabytes of DRAM.
Crazy.
Anybody that's seen a DIMM and even a 128 gig DIMM, and try to imagine that fitting that into an SSD, as well as 150 terabytes of flash, and then all the power, and that just doesn't work. That's not possible. Mm-hmm. So breaking some of those traditional views on how to do this literally made things possible that weren't before. Now, 10 years ago, you didn't have 150 terabyte flash modules, so you didn't kind of worry about these problems. But again, plan for success, plan for the future, and really embrace these trends, and you can see how this has kind of come into its sweet spot, breaking through those barriers. Performance actually follows kind of the similar pattern, right? Because instead of spending a lot of time to do garbage collection behind the scenes, manage that map and keep it updated and keep it reliable, again, we just literally don't do those processes at all. And the drive has a lot more resource in order to perform. And so all it does is reads and writes according to direction from software. So this is a great co-design example, because if you can get a bunch of junk out of the middle and the hardware just does exactly what software wants, super deterministic, performance just happens. And so now we have a lot of excess performance that we can use to perform, or we can use to generate efficiency, energy efficiency in this case, if we choose to not drive it so hard.
So I think that the piece there, and this is, And I was resisting flipping slides a little bit because like, we're just going to park here. It's like we've talked publicly about that 1 to 1,000 ratio and breaking that. That's why we put out publicly. And even I think for you, Pete, there's even like, it's my job to deliver on some of this. Like we're talking about, 150, 300 terabyte SSDs by 2026, a couple of years out. It's past anyone else's roadmap. There's pieces there about how removing that layer dramatically reduces the write amplification, which leads to much longer endurance. While your flash modules last that long, that's what underpins part of our flat and fair maintenance. We don't spike maintenance prices in year 4 or 5 or 6 or ever, because we actually have the underlying physics to economics to do that. The energy efficiency then sometimes can almost seem too good to be true, but you pull that stuff out, the lower amount of DRAM, even as it grows, not just today, 2 to 5 times better than other all flash, but it's only going to get better. And of course, I actually stole my own thunder. I was already talking about reliability, but we had it there. So the entire Pure portfolio, I want to make clear, it's powered by what we're talking about here today. It's been a transition over time, but everything, whether it's latency optimized platforms, throughput optimized platforms, cost capacity optimized platforms, it's all powered by this fundamental engineering kind of thing. Any last thoughts there before we move into the final section?
Yeah, the one that gets less attention, but I think could possibly be the most important. And when I talk to folks, I spend a lot of time talking with folks that develop essentially hyperscale systems, right? Yeah. Those are people that really understand. Of course, they understand economics, but scaling relies on that reliability portion. And the cool thing there is the reason it can be so much better than a traditional hard drive or even an SSD is that it's simplicity, and that at Pure, that's a mantra. But by removing almost all of the complexity out of the drive, we're finding that it's remarkably reliable. And this is one of the things that I was touching on, where we claimed that would be true. Now we have years and years of evidence that it's certainly true. And that means you're not replacing something every day. Your encoding schemes can be much more efficient. Mm-hmm. That gives you dividends in terms of performance and rebuild times. It just keeps giving back. And the maybe the best part about it is because the reliability of an SSD is usually determined by firmware. People think about flash and how flaky it is, and it's actually generally bugs. It's firmware getting too busy and then running out of resource and falling. That's the kind of traditional SSD failure mode. Our firmware is 10 times simpler, but that's still true. Is that it's generally not flash that's causing these to fail. And what that means is, as these things scale to these very, very large capacities, they're still reliable. So they're not becoming less reliable as they scale. And that just gives you magic in terms of getting to really large failure domains. I mean, we work with petabytes all day long now, but we're doing exabyte type deployments. Yeah. Those are staying sane because of this, fundamental underlying quality and the reliability that comes from it.
Awesome. I think we're going to close up. And for those listening in, you're like, well, we're getting close to 45-minute mark. We're probably going to cheat and go to about the 50-minute mark after the hour, so we get into the last section. And I will end the second poll and share the results back here. So just in case you're wondering, this is actually a pretty decent distribution here. There's a clear 10 to 20 terabytes is the winner, but, right behind it, 5 to 9.9. I tried to do the answers so it worked, it wasn't confusing. And we have 35% of folks where disk is still the main data storage device. Actually, the majority is yes, but only for specific things. We're going to probably tease that out a little more. But a healthy percent, I'm done with disk. Down with disk. No more of that. Olivia, if you don't mind launching the third poll. And then here we go. So looking at direct flash benefits, curious what is the most impactful for you. You can put more in the chat, please feel free. I actually love the comment from Tim about, replaced all the NetApp and EMC and haven't looked back and seen the benefits of what all we just talked about. That's great. Before today, did you know that Pure had an E family? We're going to talk about in the next section. And what do you think the E means? And you can have fun with the answer if you want to. So, it's not like we're doing this for a grade. The last section. In some ways, this is a little bit of fun when we talk, or maybe even foundational architecture up. So some of this should make a lot of sense. So three big items we want to hit on, relatively briefly, and almost it's not meant to be anticlimactic, but all of this should make sense. So the first one is at Accelerate, and even before that a little bit, we announced some pretty large direct flash modules. What are the highlights here to you, Pete?
Well, they should be obvious since we put them in giant hexes here, but
yeah,
this is taking our fundamental advantage, and based on the chart you showed and this kind of stuff, we're pushing our advantage, right? 75 terabyte QLC drive is the biggest in the world, undoubtedly, right? And by a lot. And we're going to push that further, but today this is what we've been able to do. And honestly, it takes a while for, again, all the rest of the systems to adapt to some of these capabilities. So that's the sweet spot now. 36 terabyte TLC is the biggest TLC drive in the world too. And so again, those two kind of travel together. They will for a long time, but that capacity and high density that derives from those really gives us a ton of system benefits. The energy efficiency, it's always been near and dear to my heart. It's always been important for technology, but it's become critical, right? Especially in some parts of Europe. Fortunately, the US is waking up to the benefits. Everybody, especially if you're out there in triple digit temperatures today, everybody is aware of these problems, and energy efficiency is one of the main solutions to that problem. And so we're great at energy efficiency, and then able to take big strides like this really makes things, it's a game changer in terms of how data centers are designed, and how much you can get done in your infrastructure. Of course, performance has to keep going up. That's always going to be the story. And one thing we didn't really talk about much, but we have systems that used to have a dedicated NVRAM function. And it's a super critical part of the system to keep things reliable and performant, but it takes up a lot of space. And what we've done is fold the NVRAM function into the direct flash modules so that there's a little bit of NVRAM everywhere. And now it scales really well. As the system gets larger, you get more and more throughput, you get a little bit more capacity. And because of the advantages there, we've really emphasized that, and we've doubled the capacity and performance of that function within the direct flash module. And so all of these are focused on making the systems better, and they're all directed at solving customer problems. But it's been a really nice transition to this new generation of technology.
We've got a path further. Item number 2. And this one to me was interesting because it can almost be a little bit anticlimactic sometimes. And I've worked as both as a customer and a partner. Sometimes it's like, we have to talk about the new hardware because unless we get you excited enough about it, you won't do all the work to get to it because it's going to be so painful to move everything out. And insert the word evergreen here. We've discussed that a lot here, but there is, because it took a lot of work on your and your team's end, Pete. So I don't want to diminish it with the anticlimactic side. FlashArray X R4 generation, the 4th generation of the X. Taking the C, like it says there, increased performance at 0 extra cost. If you're an Evergreen Forever customer, you will eventually get these at your Evergreen refresh cycle. And obviously we put the highlights on here, but if you had to pick 1 or 2 highlights for this announcement, what would they be?
Yeah, for me, this is like the 7th or 8th. I don't know. I lost count. And they do keep us on our toes. It's again one of the fundamental differences that we're providing is ability to upgrade at a fast pace without without any disruption, and keep the infrastructure modern all the time. It's a mantra for us, and it's not just a marketing or a business process. It's fundamental to the architecture, both in software and hardware. Another great example about how all those things really need to work together. So this transition, even though we've done it before, is super exciting, and it says it right here. This is the largest single leap we've ever made in terms of performance. And so we're able to extend the value of the platform. Folks can upgrade in place and get a really worthwhile bump in performance while we're scaling up the capacity. Sometimes those need to go together. And so for X, I think that's the story here, is you can make this transition without disruption, and it's a really significant change to the capability. The story for C, I think, is a little different. C is newer. Again, that's our lower cost. It's based on the QLC flash that we talked about.
Mm-hmm.
But it's probably 4 years old now. We started with one model. We went to 2 models, and this transition to R4 is a recognition of that success, that it's got more models. I think it's got 3 models now, but they make a significant increase in the top end capacity. They are actually more performant as well. And so for me, that's really bringing the C from, hey, this should be important, to like, wow, this has really been a huge success. Let's bring it into the full scale mainstream.
Mm-hmm. So with that, you'll see there are various, and we do this because we send out the slides afterwards. There are various FlashArray X models, and you see some of the use cases listed there. Various FlashArray C models. There's 3 models now on the FlashArray C line, matching the numbering of the X line, although it is more capacity focused, or call it 2 to 4 milliseconds. Or we used to say FlashArray C was performance focused until we announced both FlashBlade E and FlashArray E, then at Accelerate. And this is where this is the first time that we've actually had a family between FlashArray and FlashBlade. Maybe Pete, I'll give you kind of last thoughts here before I summarize down on what's exciting about the E family, both the FlashArray and the FlashBlade side.
Well, fundamentally, that trend that pulled us to do the C, to do larger and lower cost systems, even if they don't need to perform at the same level. Mm-hmm. Again, we're trying to replace disk, and this is the terrain of disk, and this will be the thing that does replace disk. But also internally, last year we did FlashBlade S, which was a huge improvement and in the FlashBlade product line. We were able to put direct flash there and get a lot of commonality there, which is great for, not just for the technology, but it's great for our team to be able to focus on a fewer number of things and make the quality better. But now we're able to kind of join those things together and bring those 2 product lines together and kind of create this continuum, because to get extremely large, you really want that FlashBlade architecture, and the picture here doesn't do it justice, because that thing can get can get physically big as you get to these huge 10 and spoiler, in the future we're going to go to 20 petabyte namespaces. That's amazing, right? But that's what the FlashBlade architecture is, the sweet spot. Wow. But below this transition, kind of around the 4 petabyte number, that's where FlashArray E does a better job, right? And so scaling down into the FlashArray architecture, that's a sweet spot there. We don't want to try to force one into the other or do something unnatural. So let's tie them together. You can understand the pricing very easily. You can get a lot of common functionality, manage those together from our management plane. And it's a big happy family.
Like it shows there, for instance. So there's a family that goes across. Sometimes look at it as previously showing more of a technical slide that showed how direct flash is underneath everything, whether it's a performance, a blend of performance capacity, or toward total focus on capacity, and frankly economics. We've been weaving the cost theme throughout this. I do want to make sure to give it a shout out on the FlashArray side. We were now I want to say it's 8 to 10 years into that chassis. It's pretty amazing the lifespan that we've gotten out of that chassis. You can kind of see some of the workloads here. I'm not gonna try and summarize that. I think that brings us to the end here. Thank you, Pete, so much for being an amazing guest. Don't leave yet. We're going to do a little bit of Q&A afterwards. So, hopefully I still got you for a couple minutes.
Well, thank you for having me. It's been fun as always.
Thank you. Really appreciate it. I knew it would be, and if anything, it's always like there's more good stuff to talk about. So we could have made, for those who are wondering, we could have made this twice as long, actually. I think you would have enjoyed it too, because there's a lot of good stuff. If you were staying around for the drawing, just in case that's you, Brendan L. from Ontario, you are the winner of an Ember 12-ounce travel mug, retail value, I believe it's $130 or whatever Amazon says right now. It's the kind you can control with your phone because, hey, that's cool. And it's actually kind of useful too. My wife appropriated mine because she drinks a lot of tea, but I have friends, my Fiona and Mia Savas, who uses his on a regular basis. Please make sure to join us next month for Data Center Fatigue Need a Cloud Bridge. Make the cloud fit your business. We'll be joined by Jack Hogan. And we'll take the last 5 minutes here to do a little bit of Q&A. I think we can kind of virtually let our hair down. I think for both of us, we both have the same hair letting down actual capability, but we'll kind of pretend to do it. Let me close up and share the first poll here. For anyone who is staying around, we are now officially done, but there's some great questions in the chat. I'll pull up here in a second. But if you were wondering, sharing the results with you, looking at direct flash benefits, what's the most impactful for you? I think, Pete, it's interesting. Performance is number one, but it's also kind of spread out. So hopefully this is interesting for you.
It is.
I see. And then before today, so a good number of folks follow along with Pure. Cool. But for 30% of you, we'll let you know something you didn't know. Cool. That's part of the point of this format. And then what does the E stand for? I'm very disappointed that only 4% voted in extraterrestrials, especially I think there's going to be like congressional hearings on this stuff soon, or I've just been watching the news there. So, but economics, efficiency. What's your vote on that one, Pete? What's your favorite of the options?
I was actually really disappointed. I wasn't able to vote. So we got to fix that. But I like the energy one is near and dear for me. But when we did brainstorm this, it meant all of those things.
Mm-hmm. Even maybe extraterrestrial. There's some magic inside.
Yeah.
So I'm thinking here, we're going to do a couple questions. And this one, it may only be two here because one is actually about, we talked about this actually last month, but it's the accelerator card that now starts to come standard in that, the hardware dedupe accelerators. And someone was asking, kind of what are they? They are a custom piece of hardware that we've written. Anything that you want to comment there, Pete, just around the direct compress accelerator card? I think I got the right name.
I think so. Yeah, that one was, I thought that was a really special project. So we started by saying, we've got a gentleman here named Jorn that he went all the way. He went into compression so deep. It's a critical technology for us, but I love that we were able to have somebody like that go. He became one of the top compression people in the world by studying the problem and came up with fundamentally better compression algorithms. With compression, you can get better and better and better compression as long as you're willing to spend CPU cycles. And it's a really classic like diminishing return problem because you got to spend a lot more cycles to find that next little bit of compression that's available. And by improving these algorithms, he actually made it much harder to compete with hardware because he made the software algorithm way more efficient. And so it's one of those moving targets where if you aim at the old target and somebody moves the arc forward, you're gonna miss. But what we did was we took the new algorithms, we implemented in software, and we also implemented it in hardware. But these algorithms tend to have like deeper levels. So we did a deeper and deeper level that we could then get the best of both, better compression, but we also offloaded the CPU at the same time. And so this was a great system view where you look at what's consuming a lot of resources in your system. But hey, we also want to push that part of the capability forward. And this was a great application of that technology. And we're going to do more. There's a lot of other areas that are similar where we'd like to offload and we'd like to do it with specialized hardware.
I think with that, we are at 59 minutes past the hour. We always kind of hang around the full time with questions, a little less questions this time. Maybe actually I'll just do, are you good for another couple minutes, Pete?
Sure.
Or should I wrap?
Yeah, of course.
I'll toss one last question at because it was actually just a really fun one. And let me actually see if I can find it back here now. It was from, there's been comments about reliability of direct flash and what they've been seeing with Pure systems. So a question from Shalin, if I got her name right. And it was really, what did 25 to 30 year ago, Pete, or maybe 10 or 15, what did you see as major developments? and there are things that you thought that might play out that didn't, or things that you thought that wouldn't play out but did, kind of a little bit of like, kind of Pete's view of the world of 5, 10, 15 year ago, and how it's shifted or not.
Yeah, well, I mean, 30 years ago, Pete was, concerned about, skiing versus snowboarding or something like that. Again, I used to have a lot more fun, but yeah, I don't know. These transitions keep coming, right? And so 10 years ago, we talked about some of those transitions, but I think the fundamental one, even before I joined Pure, was this flash revolution, right? And again, you look at every aspect of it being better, except cost, and cost coming down, and techniques like that we've talked about to further that cause, and that just changed my life. I decided to focus on the technology. I decided to join Pure and then ride that trend. But there's things like that in every area. We saw AI emerging at that time, and AI has been around for 30 years under different names and different abilities, and works for the little different things. But it was about 10 years ago, maybe 11, that really took a big inflection point, right? And now look at us. It's some circles, that's all we talk about.
Yep.
Certainly, we spend a lot of time optimizing systems for those workloads now, and it's even changed the definition of compute for a lot of folks. And you don't think about a CPU anymore, but you might think about TPUs and GPUs and how to apply them to these different kind of workloads. And so that one's been exciting. We work a lot in that area, and it's affected people that I know that aren't in technology, which is also kind of fun, right? Kind of all aspects of life.
Actually, I was joking a little bit with Calvin. He handles a lot of our solutions marketing around AI, and we were pulling forward the cowbell meme that, everything, if you want to go do that, the more cowbell, the great SNL skill. Everything needs more AI these days, right? Kind of thing.
That's right.
Okay, I think with that, we're going to call it a wrap. Hey, thank you once again for even staying a little bit longer, because I wanted to toss that in. Please make sure to join us next month. I won't say the title again. You can see it on there. You'll get that. Yeah, everyone can use more cowbell. Absolutely right, Tim. Kind of thing in the chat there. Thank you again so much. I will turn the music back up, and we will, on behalf of Pete Kirkpatrick, thank you for joining us. And Pure Storage Coffee Break, thank you so much for joining us today. I hope you have a great day, a great week, and I will see you next month.